the mic and read the question here, which is given in 2000 AL. It is the second structure essay question given in 2000 AL paper. Somebody unmute the mic and read the things, read the question here.
The figure shows an apparatus arranged by a student in the laboratory to generate steam. The tube B is used to take steam out. Simple A. In this setup, the two tubes A and B are fixed incorrectly. State how would you arrange them properly?
Yes, they are very good. Thank you, dear. The tubes are not connected properly. They are not arranged properly. What are the upsets there? What is the upset with tube B here? It is not properly connected. Can somebody unmute the mic and tell me the upset with the tube B? This one.
They should be sink in the water.
B is sink in water. So will steam flow through the tube B here?
No, sir.
No. So we should do something like this. Tube B is immersed in water. So we should take the tube B, low end of tube B should be at above the water surface. Can you understand? If tube B is like this, no problem. Now what do you think here? Low end of tube B should be taken, should be kept above the water. State how would you arrange them properly? So what's the first thing that we should do here? What's the first thing that we should do? The lower end of tube B is kept above the water surface. Am I right here? It should be kept above the water surface. Or we should move the tube B upward. Tube B should be moved up. What is the next upset here? What is the next upset here? If tube B is kept, if the low end of tube B is kept inside the water, steam will not coming out to the tube B. What is the upset with the tube A? Somebody unmute the mic and tell me.
A should be immersed in the water.
Yes, A should be immersed in water. Otherwise, what will happen here? Otherwise, steam will flow through tube A. Tube B is bent and tube B will be connected to the steam trap. So for the steam, it's very difficult for steam to flow through the tube B. So steam will directly flow to the tube A. So we shouldn't, if we say just we should immerse tube B, we should say something like this. Listen. Actually, the lower end of tube B should be immersed in water like this. Can you see the figure here? So this is what you do. So what's the second thing that we should do? First thing is low end of tube B kept above water. And number two, let me write number two. The lower end of the tube, lower end of the tube A immersed in water. Can you see my answer here, Lamai? Hello? Lamai, can you see my answer?
Yes, sir.
Yeah. So write the heading. What is the heading? You should write the heading as 2000 AL second structured essay question. 2000 AL second structured essay question. This is the answer for simple A question. Okay, dear. So please write the question numbers properly and write down your answer. Start. Write them there. Shall we go to the next question? Who wants more time to write there? Shall we go to the next question, Lamai? Just tell me yes or no, quick.
Yes, sir.
Yes, very good. Thank you. So let's go to the next question. I'm going to erase this. If you want any more time to write, just take a screenshot. Just take a screenshot. Right, simple B question asks, what is the purpose of having tube A? What is the purpose of having the tube A? Many of the students say to reduce the pressure. To reduce the pressure. No, actually tube A is used. We are not interested in maintaining any pressure. Tube A is used for the safety. For the safety. If pressure is highly increased, there's a possibility to push this knob. To push this knob upward, so that will be very dangerous because steam will come out and people will be burned. So why do we use tube B here? For the safety of the people. Otherwise this lid will be moved from this boiler and hot steam will come out. Hot steam will come out and people will be burned. Okay, so therefore tube B is used for the safety. Right here. Simple B, answer for simple B question for the safety. For the safety. Right, now let's go to simple C question. Let's go to simple C question.
Excuse me, sir.
Yeah.
Sir, but what is the real purpose of tube A?
For the safety dear.
So that means removing excess steam?
Sorry, I didn't hear you.
Does that mean by removing excess steam?
No, dear. It is something like this. Okay, if you I explained it. Were you in the last week class, dear?
No, sir, I lost connection.
Okay, let me explain for you. Listen to me. So tube B is kept like this. Listen, if we consider tube A, I'll help you, don't worry. So tube A is immersed like this, right? Now we provide heat energy is continuously provided. Heat energy is continuously provided. So due to the provided heat energy, temperature of the boiler increases, right? Then more and more steam is generated here. More and more steam generated here. So then the pressure inside the boiler will be highly increased because we provide heat energy. That heat energy converts water in the boiler into steam. So huge amount of steam is created here. Only part of that generated steam will flow to the tube B. We take part of the steam we are taking out from the tube B, but there will be some more steam inside the tube B. Inside the boiler. So then the pressure inside the boiler will be highly increased. Then this lid may be pushed out, thrown out from the boiler. If this lid is not there, what will happen there? If the lid is at once removed, if there is no such a lid, what will happen? All the hot steam will flow out from the boiler at once. All the hot steam will come out at once. And that steam will burn the people who are doing the experiment, who are continuing the experiment. Can you understand here? So if somebody is here, if somebody is closer to the boiler, right, he will be burned. People will be burned. So we should guarantee the safety. We should guarantee the safety of the people who are doing the experiment. Therefore, we use this tube B, right? Then I should explain how this tube B stop that danger. How this tube B stop it? Are you okay? Can you understand? If steam comes out, what will happen? That steam will burn the people and it is dangerous. Therefore, we should do something for the safety of the people. Are you okay up to the that point?
Yes, sir.
Right. Now I should explain how this tube B gives us safety. Right. It gives us safety like this. Listen. Tube A. How this tube A gives us safety. So when we provide heat energy, to this water, right? When we provide heat energy to water, temperature of water increases. Water is here and water is there. Temperature of water increases and steam generates. So at a certain time, when the pressure here increases, that pressure pushes this water down, and that water will flow upward through the tube A. Can you understand what happened?
Yes, sir.
Then we can observe that some of the water in the boiler, right? Some water in the boiler flows upward through the tube A. What does it mean here? Now we know that pressure inside the boiler is highly increased. That's why this water flows up through the tube A. Then what should we do? Even if this water comes out, there's a possibility for people to burn from that water. So what should we do? Now we have observed that water is rising up through the tube A. So what should we do then?
We have to collect the water.
No, dear. Yeah, we can collect the water, but in this experiment, we do something like this. We take this burner out from the boiler. We take the burner out. Can you understand it? Once we take the burner out, what will happen? Then no heat is provided to water. Right? But still there is some steam. Still there is some steam at under high pressure. Therefore, we still get steam from the tube B. We have taken the burner out. We have taken the burner out. But still there is steam inside the boiler under high pressure. That steam cannot flow through the tube A because tube A is blocked by water. Tube A is blocked by water. Therefore, that steam has to flow through the tube B. Therefore, we take some steam out from the tube B. Therefore, flow of steam will not be stopped. Once we take the burner out, no further heat energy is provided to the boiler. Therefore, pressure inside the boiler slowly reduced. Then we can observe that the water column in the tube A. Water column in the tube A is now again falling down. Water column in the tube A is now again falling down. Once that water column completely falls down, we keep the burner again in this side. Again, we keep the burner in. Then again, burner provides heat energy. Then again, steam generates. Can you understand here? Can you understand the procedure?
Yes, sir.
Right. So we use tube A. We cannot write all these things in the examination here. We cannot write pressure will be increased, steam will be coming out, people will be burned. Then we should take the burner in and out. We cannot write all these things because this is structured essay. They will give you only one line. They will give you only one line to write the answer. So within one line, we cannot write all the things. We short and sweet answer is written for the safety. Okay, dear?
Okay, sir.
Right. What about others? Are you all okay with the answer and explanations?
Yes, sir.
Right. If so, shall we go to the next question? Right. Let's go to question number 6. Sorry. Somebody unmute the mic and read question C. Quick.
After making the changes mentioned in A, the student decided to use the above setup to determine the specific latent heat of vaporization of water by inserting the outlet of the tube B directly into the calorimeter C containing water. This procedure is not satisfactory. Roman number 1, explain why. Roman number 2, the correct procedure in this experiment would be to connect another piece of apparatus to the outlet of tube B before passing steam into the calorimeter. Draw this piece of apparatus in the space between the tube B and the calorimeter.
Right. Thank you very much, dear. Thank you very much. After taking the changes mentioned in A, so it means by changing the tube positions of the tube, a student used this arrangement to determine specific latent heat of vaporization. But he does a mistake. What is the mistake done by this student here? Outlet of tube B directly insert into the calorimeter containing water. Right? So what is the upset with this method here? If we directly insert the tube B into the calorimeter, what will happen here? Somebody unmute the mic and tell me.
The droplets enter the hot water.
Yeah, very good. When steam flows to the tube B, some of the steam may be condensed and make hot water drops. So, it is not satisfactory. This procedure is not satisfactory. It's not good. So we can write that the condensed steam, steam, within brackets, hot water drops will be added to the water in calorimeter. So this is the answer. Please write this answer here. Please write exact. You should write the answer exactly like this in the examination, right? This is the method. Please write your answer. Please write the question numbers properly. Simple C, Roman number 1. Write the answer here. The condensed steam, within brackets, hot water drops will be added to the water in the calorimeter. Okay. If you add this, tube B directly into the calorimeter, there will be, when steam flow through the tube B, some of the steam may be converted into liquid water. That liquid water is known as condensed steam. That condensed steam or hot water drops will be added to the calorimeter water. So some people are, so what's the upset when water added? So here in this practical, we want only steam. We do not want hot water drops. We need only steam because we are going to do calculations with steam, but not with hot water drops. We want to find the specific latent heat of vaporization of steam, right? We want to work with vapor, steam. We don't want to work with hot water drops. So we should take only steam without any water drops. Okay, dear? Right, see, Roman number 2. The correct procedure in this experiment would to connect another piece of apparatus to the outlet of tube B. The correct procedure in this experiment would be to connect another piece of apparatus to the outlet of tube B before passing the steam into the calorimeter. Draw this piece of apparatus in the space provided between the tube B and the calorimeter. What is the name of this gadget here? Somebody please tell me the name of this gadget.
Steam trap.
Sorry?
Steam trap.
Steam trap name. Steam trap. How do we draw it? Lamai, how do we draw it? Can you see the board clearly? Lamai, can you see the board clearly?
Yes, sir.
Right. So, This is the calorimeter. We should connect something so called steam trap. Let me give a try to draw it. So a steam trap is something like this, right? Its shape may be something like this. So we should the steam flows through this tube. Steam flows through this tube, right? The size will not be enough. So I'll do some. You can draw a steam trap in different ways. So if you want, you can connect the steam trap like this. And let me take steam out from a tube like this. So this is the arrangement. This arrangement is called steam trap. But connections are blocked. So let me remove the connections. Okay, and here, right, and this one. Okay, dear. I think no need to draw the entire figure. Can you draw this, dear? Can you complete this quick? So this part is called stream trap. This is calorimeter. If you wish, you can draw the entire figure also. If you are a good student, if you are not lazy, you can draw the entire arrangement at home. Yes. Is the time enough for you to draw the figure here? Lama, is the time enough?
Yes, sir.
Right. If you want any more time, just draw it, right? So this is calorimeter, this is boiler, burner, right? And if this is your first day, we have kept a heat insulated sheet here, which is called steel trap. So this kind of things were there. And this is the calorimeter. This is another calorimeter, bigger calorimeter. So these are some heat insulate. Sorry. So these are some heat insulating supports. They stop the heat. They stop the heat flow from calorimeter to the outer calorimeter. These are actually wood. These two triangular shapes are made of wood. This is a calorimeter. The other one is a larger vessel. So there is an air layer around the calorimeter. It stops the it stops direct heat loss to the surroundings. Right. This arrangement, this larger vessel, and this calorimeter is kept inside the larger vessel. That stops the heat loss to the surroundings. So that kind of things are there.
Right. We have discussed up to first we completed tube A is used for safety. Tube B is used to take steam out. Low end of tube A should be immersed in water, and low end of tube B should be kept above the water level. Right. Tube A is used for safety. See, after making the changes mentioned above, the student decided to set up to determine specific latent heat of vaporization of water by inserting outlet of the tube B directly into the calorimeter C containing water. This procedure is not satisfactory. Explain the reason. The reason is there is a possibility to come some steam may be condensed, and that condensed steam will be added to the calorimeter as hot liquid water drops. So that's why that's a possibility for hot water drops to be added to the calorimeter. That's why that procedure is not satisfactory. Roman number two. The correct procedure in this experiment would to be connect another piece of apparatus to the outlet of tube B before passing steam into the calorimeter. Draw this piece of apparatus in the space between tube B and calorimeter. So that is steam trap. We have already drawn it. Steam trap. We have already drawn it. Simple D question. In addition to the two relevant temperature measurements, what are the other measurements that you would take in this experiment? In addition to the two relevant temperature measurements, what are the other measurements that you would take in this experiment? What are the other measurements that we take in this experiment here? Can somebody tell me?
The mass of the calorimeter?
Yes, actually the mass measurements are taken. What are the we take? Actually, we should take 3 mass measurements, right? What are the 3 mass measurements there? First, we should measure. There are 3 mass measurements should be taken as 1, 2, and 3, right? There are 3 mass measurements. The first mass measurement is the mass. Please write with me. Put the question number D, simple number 1. The mass of empty calorimeter with the stirrer. So you should remember that calorimeter and stirrer should be made with the same material. If the calorimeter is made of copper, stirrer should also be measured with copper. Okay, the same material must be used. The second mass measurement is the mass of the calorimeter. With the stirrer and cool water. Am I right, dear? Right. Those are the mass measurements. What is the third mass measurement, dear? Somebody unmute the mic and tell me. What is the third mass measurement? Somebody unmute the mic and tell me.
The mass of the calorimeter with the stirrer, water, and condensed steam.
Very good. Excellent. The mass of the calorimeter with the stirrer, water, and condensed water. Right? So please write them there. Shall we go to the next question, dear Lamai? Do you want more time, or shall we go to the next question? Somebody unmute the mic and read simple D Roman number 2. Somebody unmute the mic and read simple D Roman number 2.
What additional data do you need for after computation of specific latent heat of vaporization of
Very good. Thank you, dear. What additional data do you need of the computation of the specific latent heat of vaporization of water? What are the other data that we want, dear? We know the 3 mass measurements. We know the initial temperature and final temperature. What are the additional data that we want, dear? Lamai? So this is the answer for simple D Roman number 1, right? D Roman number 2, they ask what are the additional data that we want. Can somebody tell me? Actually, we want 2 more data. Can somebody unmute the mic and tell me the 2 data that we want?
Specific heat capacity.
Very good. Very good. We want specific heat capacity of what? Complete. Specific heat capacity of
The calorimeter.
specific
Water.
Yeah, we want both actually. Very good. Specific capacity, specific heat capacity of water. Second one, specific, talk to me, dear. Specific heat capacity of
calorimeter?
Yeah, actually we should say it slightly modified, slightly edit the answer. Specific heat capacity of material of the calorimeter, as well as the material of the stirrer. Specific heat capacity of material of the calorimeter. Got it? Please write the answer here. So that is the answer for simple D Roman number 2. Lamai, shall we go to the next question? Okay, let's
Okay,
go to
sir.
the next question. Right. Somebody please unmute the mic and read simple equation. Unmute the mic and read simple equation. Please speak a little bit loudly. Okay.
What precautions would you take in order to improve the accuracy of the experiment?
Very good. Thank you very much, dear. So what are the precautions that we take in this experiment? Precautions mean the things that we did before we start the practical. What precautions would take in order to improve the accuracy of the experiment? The first precaution is the experiment starts with cool water and finishes when water reaches few degrees, or we can say and finishes with hot water. Let's say and finishes with hot water. That's enough. Why is that, dear? Can somebody tell me the reason? Why did we start the practical with cool water and why did we stop the practical with hot water? Can somebody tell me the reason? Lamai? Can somebody tell me the reason which is known as cooling correction, but you must explain. This is known as a cooling correction, but you should explain. Somebody please unmute the mic and explain the reason for us to start the practical with cool water and stop the practical with hot water. You must try. If not, I will not continue the class. Okay, very good. Some of the students had sent me the answers to the Zoom chat. The reason is to neglect or to prevent heat loss to the surroundings, or to make the net heat exchange with the surroundings to be zero. To make the net heat exchange with the surroundings to be zero, or to neglect the heat loss to the surroundings to be zero. Right. The second precaution is a heat shield. A heat shield is kept in between. A heat shield is kept in between burner and the calorimeter. Burner and the calorimeter. Okay, dear. So those are the precautions, the things that we do before we start the practical and to increase the accuracy of the practical. Okay, dear. If we do a heat shield, mean a heat insulating sheet is kept between the calorimeter and the burner. It will stop direct heat flow from calorimeter burner to the calorimeter. Right. So I think that's the end of the question, right? So please try this question again at home. Repeat the answers, then only you are okay with this, right? As I remember, I have completed 3 practicals so far. So we should go to the next practical, the fourth practical. There are 10 practicals in physics syllabus, in heat lesson, or you can say thermal physics, whatever it is. So there are 10 practicals. So we have completed 3 practicals and we have answered 3 past paper questions given from each of the 3 practicals that we have discussed. So today I wish to start the 4th practical. Right. If you want any more time to write, please take a screenshot. I'm going to erase everything. If you want any more time to write the things, please take a screenshot. I'm going to erase everything. Lamai, there is another section. There is another section. There is one more question in 2000 AL first, heat structure disequation. Simple left question. Somebody please unmute the mic and read the question simple left here. Unmute the mic and read simple left question. I think we were disconnected. Is video okay now, dear? Lama, is video okay?
It's blurred, sir.
What about my voice? Can you hear my voice clearly?
Yes, sir.
Right. So I'll read question simple left. Listen to me carefully. When the above experiment was carried out in hill country school laboratory, the barometer reading was found to be 720 millimeter of mercury. What is a barometer here? What is a barometer?
A measuring instrument of pressure.
Would you please tell me what a barometer is?
The instrument used to measure the atmospheric pressure.
Yes, very good. A barometer is an instrument which is used to measure atmospheric pressure. So what is the normal atmospheric pressure in mercury millimeter? It is approximately 760 mercury millimeter. But what is the atmospheric pressure in the hill country? Hill country means areas in Kandy, Nuwan, like that, right? So what is the atmospheric pressure in that school, dear? The atmosphere around that school. Somebody please tell me.
720.
So, which is it larger than normal atmospheric pressure or smaller than normal atmospheric pressure?
Smaller.
Atmospheric pressure is smaller. Very good. So, if the atmospheric pressure is smaller, water boils less than 100 degrees Celsius. What is the point there, Lamai? Somebody unmute the mic and tell me the reason.
Because of the high altitude?
Yeah. At high altitude in hill countries, atmospheric pressure is less than the normal atmospheric pressure. When the atmospheric pressure is less than, the boiling point of water is reduced. Now water boils something like 90 degrees Celsius, 95 degrees Celsius, like that. Clear? So if for example, let's say water boils at 90 degrees Celsius, then what is the temperature of steam? Can you tell me? Due to the low atmospheric pressure, water boils at a smaller temperature than 100 degrees Celsius. Then let's say temperature of water, boiling point of water under this condition, let's say 90 degrees Celsius. Then what is the temperature of steam here? Somebody unmute the mic and tell me. I think you heard me, even though we were disconnected again, right? My question was, the experiment was carried in Hill Country School lab, right? Therefore, atmospheric pressure in the Hill Country is less than the normal atmospheric pressure. Due to the lower atmospheric pressure, water boils at a temperature less than 100 degrees Celsius. So I have asked you to assume the boiling point of water at Hill Country to be 90 degrees Celsius. So my question was, then what should be the temperature of steam? Somebody unmute the mic and tell me.
Lower than 100 degrees.
You lower than 100 degrees Celsius, but at once you should be able to tell me the value, numerical value. What should be the temperature of steam now?
90.
90 degrees Celsius, very good. If water boils at 90 degrees Celsius, the temperature of steam should also be 90 degrees Celsius. Therefore, in the calculations, we should use the temperature of steam as 90 degrees Celsius, right? But to find the temperature of steam, we have to measure the temperature of steam. Or we can do something like this. If we have a chart which gives the boiling point of water under different temperatures. Let's say there are some graphs, charts, data sheets, data books. From them we can find the boiling point of water under different pressures. So here the pressure is 720 mercury millimeter. So from a data sheet, we can find the boiling point of water under this pressure, right? And that temperature should be used as the temperature of steam. Is it clear, dear Lamai? By using a data sheet or a chart or a graph, we should find the correct boiling point of under this atmospheric pressure. And that temperature should be used as the temperature of steam. Now let's write the answer. The correct boiling point of water should be found under this atmospheric pressure. Under this atmospheric pressure. The correct boiling point of water should be found under this atmospheric pressure. And that temperature should be used as the temperature of steam. The correct boiling point of water under this atmospheric pressure should be found. And that temperature should be used as the temperature of steam. Is it clear for all, dear? Right. Or we have to connect a thermometer to the boiler and we have to find it. So you can use a data sheet or a thermometer, additional thermometer in the boiler. But in school lab, we do not have so many thermometers. So therefore, the best thing is using a data sheet. Right. Now somebody unmute the mic and read my answer. Unmute the mic and read my answer. Start.
The correct boiling point of water should be found under this atmospheric pressure, and the temperature should be used as the temperature of steam.
Thank you, dear. But would you please repeat it with a louder voice, dear, please?
The correct boiling point of water should be found under this atmospheric pressure, and that temperature should be used as the temperature of the steam.
Very good. Thank you very much. Thank you, Buddha. Any other student who wants to listen to the answer once again, who are not able to write the answer and who would like to listen to that answer one more time? Okay. One more student, please unmute the mic and read the answer before we go to the next experiment. One more student, please unmute the mic and read the answer, please.
The correct boiling point of water should be found under this atmospheric pressure, and this temperature should be used as the temperature of steam.
Thank you, dear. Thank you very much. But would you please read one more time slowly and loudly? And do not mute the mic at once. Once you finish the reading, do not mute the mic at once. Please read loudly and slowly.
The correct boiling point of water should be found under this atmospheric pressure, and this temperature should be used as temperature of steam.
Very good. Excellent. So I think we'll be able to make many teachers because you are reading the notes, answers very well. The professional way of reading I have observed from many of you. So it means one day, once you complete the degree, one day you will be able to be good teachers until you find a job or when you have free time. Yeah, I think many of you have good voice, a professional way of talking, so narrating things. So I think there will be many good teachers. I'm so happy with it. Excellent, Buddha. Very good. Right, shall we go to the next experiment here? Lamai, please give me the permission.
Okay, sir.
Right, thank you, dear. Let's start. Let's start. So as I remember, this is the fourth practical. Am I right, dear? Am I? And write the name of the practical as determination. Determination of thermal conductivity. Thermal conductivity of a metal rod. Determination of thermal conductivity of a metal rod by let me indicate the name of the scientist. Searle's method. Please write the heading there, subheading. Determination of thermal conductivity of a metal rod by Searle's method. Write the heading there. Right. The experiment arrangement is something like this. Let me draw the experimental arrangement. Right. We take a metal rod. So let's say this is the metal rod. Right. Please wait until I draw the complete experimental setup. Right. Please don't draw until I completely draw it. So let's say this is a metal rod. Right. In the metal rod, one end of the metal rod is kept in a steam chamber. Right. One end of the metal rod is kept in a steam chamber. So it means we send steam into a metal box which is closed. Right. So we should use two tubes to send steam. Right. So normally we send steam into the tube through the upper tube, and steam is taken out from the lower tube. So this is the arrangement. Right. Please wait until I completely draw the figure. Right. Right. Steam is sent into the chamber through the upper tube. Steam is taken out from the lower tube. I'll explain the reasons. Right. So do not worry about the reasons. I'll tell you the reasons. Right. So we send steam into the chamber through the upper tube. We take steam out from the lower tube. Okay. So somebody unmute the mic and tell me the temperature at this end. What should be the temperature at this end? Let me mark it as X. So what is the temperature at the end X of the rod? Lamai? Please don't sleep. Somebody, this is completely filled with steam under the normal temperature. Steam is kept under normal temperature. So my question is, what should be the temperature of the end X of the rod? Somebody unmute the mic and tell me.
It's equal to the temperature of the steam.
It is equal to the temperature of steam. If the steam is generated under the normal atmospheric pressure, what should be the temperature of the steam, dear?
100 degrees Celsius.
100 degrees Celsius. Very good. Right. So end X is at the temperature of 100 degrees Celsius. After that, we take some copper tubes. They are wound on this end. Right. So I'm using a digital whiteboard. Therefore, there may be some differences the way I draw, but once I complete draw it, you will understand the method I used. Right. So they are connected to each other. These tubes are connected to each other. Right. Right. It's something like this. This end of the tube is connected to the other end like this. Right. They are connected like this. Right. I think you will be able to draw the things better than me. So a copper tube is wound on the other end of the tube. Wound on the other end of the tube. Like this. Sometimes it is called a copper spiral. Copper spiral. Right? Like this. So we send water through this copper spiral. We send water through this copper spiral. Okay, dear? What do we do, Lamai? Don't sleep. What do we do? Lamai.
Send water through the copper tube.
Very good. We send water through the copper spiral. Right. To send water, we use an arrangement like this. I'm going to erase the heading. I'm going to erase the heading, or let me move it down. I'll keep it here. Right. I'll keep the heading of the practical below, like this. Then we use a cup. We use a cup like this. Right. We take a tube from this cup. Actually, we use a rubber tube. We use a rubber tube to take water. Right? And that water is given to another metal box. Wait until I complete the figure, then only you can understand it. We take water from this metal cup. Right? So this is a cup which is filled with water. That water flows through this rubber tube. Right? And that water enters to this tube. And that water will flow through this copper tube. And finally, we use another metal chamber. And water coming through this is collected to a measuring cylinder. Is collected into a measuring cylinder. Right? So you think that it's very complicated, but you will understand, you will realize that this is a very simple thing once I completely draw the arrangement. Right? So water coming through this collected into a measuring cylinder. Right? Okay. And we should cover everything by a good heat insulating material. So the rod is completely covered with a good heat insulating material. Can somebody unmute the mic and tell me why we cover this by a heat insulating material? Somebody unmute the mic and tell me the reason.
To prevent heat loss.
To stop the heat loss. Very good. This is a heat insulating material, which is known as legging. Got it there? Right. So heat energy is absorbed by the rod at the end X. That heat energy travels to the end Y through the rod. And that heat energy is absorbed by water, flows through the copper spiral. And that heat energy is absorbed by the water, flows through the copper tube. Copper tube, sometimes it's called copper spiral. Okay, dear? Right. This is a rubber tube. This gadget has a very special name. Anybody does? Is there anybody who knows the name of this gadget, dear? Lamai? Anybody knows the name of this gadget, which is filled with water, and that water will flow through this tube? Anybody knows the name? Lamai? And you know, it's not necessary for you to fill the tube like this with water, right? I just did it for you to understand, but it's not necessary to draw water like this. Anybody knows the name of this gadget here? You are very afraid to talk, right?
So I'm not sure, but it's similar to a Liebig condenser, right?
I'm talking about this one, dear.
Sorry, sir, I don't have. I couldn't hear the question completely. I'm sorry, sir. I have no idea about what that is.
Because some school teachers may have described this. That's why I thought that you know it. Okay. This is called. One more student, please give a try. You must know these things, dear. You must have heard the name of this gadget. It's a metal cup having two tubes. A metal cup with two tubes like this. Okay. Okay, I'll help you. Which is known as constant pressure head. What's the name of this gadget, dear? Lamai? Unmute the mic and tell me what is the name of this gadget. Constant pressure head. Very good. So water level will never go up because additional water will flow through this tube. Additional water will flow out through this tube. Can you understand here? Water level will never be increased. Water level will never be increased because additional water will leave the chamber through this tube. Got it? Right. Now I think you can draw it. Wait, I want to add some thermometers also. Please wait until I add some thermometers there. So here we have to make two holes. We make two holes on the rod. We have to make two holes in the rod. First hole and second hole. And we place thermometers inside the holes. This is the first thermometer. The first thermometer. Wait. Why is that? The first thermometer and another thermometer. So why do we use thermometers, dear? Lamai, why do we use thermometers? What do we do with thermometers, Lamai?
To measure the temperature.
Measure the
To
temperature.
measure the temperature. Now, if you clearly observe, there's a small gap. There's a small gap between the thermometers and the metal rod. So will we be able to measure the temperature more accurately there? You see the upset there? There's a gap between the thermometer and the metal rod. So we will not be able to measure the temperature correctly. Did you observe the gap between the thermometer and the metal rod there, Lamai? Just tell me yes or no. Please don't make me angry. Can you see that there is a small gap between the thermometer and the rod? Right hand
Yes,
side
sir.
and left hand side?
Yes, sir.
Yeah. So therefore, we will not be able to measure the temperature accurately. Then we do something like this. We fill this gap with mercury. What is the specialty of mercury here? Mercury is a metal and it is in the form of a liquid. Am I right, dear? Lamai?
Yes, sir.
So we fill the hole with liquid mercury. Got it? So thermometer is completely covered by, thermometer bulb is completely covered by mercury. Mercury is a metal. It's a very good heat conductor. Okay. Now the temperature of the metal at this place can be measured with very high accuracy. Okay, dear? Right. And we use another 2 thermometers to measure the temperature here, to measure the temperature of inlet water and to measure the temperature of outlet water. Now this is the complete arrangement. So please draw the figure. Start here. Please draw the complete figure. After that, I'll give you another description. Lamai, who wants more time, dear? Shall we continue the practical? If you want more time, please tell me, dear. I'm waiting until you draw the figure. You should mark one more thing. Please mark this height. Please mark the height of water here. This as simple H. It's a very important quantity. Mark this height as simple H. Simple H. Right. Simple H is the distance between the water level in the constant pressure head and the water level in the rubber tube. I have not named it. We must name this as, wait, we should name this as constant pressure head. Wait. Rubber tube, okay. This is the rubber tube and this gadget. That gadget is known as constant pressure head. This is known as constant pressure head. They will ask in the examination, constant pressure head. Lamai, please name them, dear. Constant pressure head. And you should name this tube as P and this tube as Q. Right. I think you have completely drawn the figure and named all the parts. So water sent into the constant pressure head, additional water will leave through the middle tube. The other tube will send the water into the copper tube, and that copper tube is wound on the end of the metal rod. Metal rod we should name. So what is it there? This is the metal rod, right? So heat energy flows through the metal rod from X to Y. Shall we continue, dear? Lamai, who wants more time to draw the figure? Shall we continue? Just give me the permission. Hello?
Let's continue, sir.
Right. Let's write there. Please put 1, 2, 3, 4 and write. Number 1. The end X of the rod is heated by using steam. The end X of the rod is heated by using steam. By using steam. As the continue, number 1, end X of the rod is heated by using steam. As the steam is generated under normal atmospheric pressure. As the steam is generated under normal atmospheric pressure, the temperature of steam variation 100 degrees Celsius. As steam is generated under normal atmospheric pressure, the temperature of steam is 100 degrees Celsius. Full stop. Therefore, full stop and continue. Therefore, the end X of the rod, reaches to a constant temperature of, therefore the end X of the rod reaches to a constant temperature of 100 degrees Celsius Therefore, the end X of the rod reaches to a constant temperature of 100 degrees Celsius. Number two. Before I go to number 2, somebody unmute the mic and read number 1. Before I go to the second point, somebody unmute the mic and read the first point loudly.
The end X of the rod is heated by using steam. As the steam is generated under normal atmospheric pressure, the temperature of the steam is 100 Celsius degrees. Therefore, the end X of the rod reaches to a constant temperature of 100 Celsius degrees.
Lamai, okay. If you read half of the first point, I'll read the next half, dear. That's the deal. Half. If you start, I'll complete. Somebody try.
The end X of the rod is heated by using steam. As the steam is generated under normal atmospheric pressure, the temperature of the steam is 100 degrees Celsius.
Therefore, very good, Buddha. Thank you very much. Therefore, the end X of the rod, reaches to a constant temperature of 100 degrees Celsius. Therefore, the end X of the rod reaches to a constant temperature of 100 degrees Celsius. Therefore, the end X of the rod reaches to a constant temperature of 100 degrees Celsius. And now somebody unmute the mic and read point 1 from beginning to the end. You know the deal. If you talk, I will also talk. If you are silent, I will also be silent. So therefore, somebody unmute the mic and read the point 1 completely.
The end X of the rod is heated by using the steam, and the steam is generated under normal conditions. The temperature of the rod is 100 degrees Celsius. Therefore, the end X of the rod reaches to a constant temperature of 100 degrees Celsius.
Okay, who would like to listen to the point again? Is there anybody who would like to listen to point 1 again, one more time? Okay, so in the examination, they will ask, why do we use steam to provide heat energy to the rod? In the examination, they will ask, why do you use steam to heat the rod? The answer is to keep one end of the rod at a constant temperature of 100 degrees Celsius. What is it? To keep the one end of the rod at a constant temperature of 100 degrees Celsius. Number 2, the second point. Number 2. The heat energy flows from X to Y through the rod. The heat energy flows through the rod from X to Y. Sorry, dear. Sorry. Heat energy flows from X to Y through the rod by the process of conduction. Heat energy flows from X to Y through the rod by the process of conduction. Lamai, may I repeat, or is it clear? Okay, I'll repeat. Is my audio clear here? Can you hear my voice clearly or not?
We can hear you clearly, sir.
Right. Thank you, Buddha. Thank you very much. So I'll repeat. Heat energy flows from X to Y through the rod by the process of conduction. Heat energy flows from X to Y through the rod by the process of conduction. By the process of conduction. Number 3. Number 3. That heat energy is absorbed by water flows through the copper tube. Number 3. That heat energy is absorbed by water flows through the copper tube. That heat energy is absorbed by water flows through the copper tube. Full stop. Number 4. Number 4. Inlet and outlet temperature of water. Inlet and outlet temperature of water are measured by inlet and outlet temperature of water are measured by T4 and T3 thermometers. inlet and outlet temperatures of water are measured by T3 and T4 thermometers. T3 and T4 thermometers. Full stop. Full stop. Next point. What is the next number here? What is the next number here?
Number 5.
Number 5. Okay, I want to help. Listen here, I want to help. Before I read number 5, somebody unmute the mic and read 1, 2, 3, 4 steps again. Loudly, somebody unmute the mic and loudly read 1, 2, 3, 4 steps. Then I'll read you number 4. Start there.
Number 1. The end X of the rod is heated using steam. As the steam is generated under normal atmospheric pressure, the temperature of steam is 100 degrees Celsius. Therefore, the end X of the rod reaches to a constant temperature of 100 degrees Celsius. Number 2. The heat energy flows through the rod from X to Y by the process of conduction. Number 3. That heat energy is absorbed by the water flows through the copper tube. Number 4. Inlet and outlet temperature of water are measured by T3 and T4 thermometers.
Thank you. Thank you very much. Number 5. Two small holes are constructed in the rod, and two small holes are constructed in the rod, and two small holes are constructed in the rod, and the bulbs of T1 and T2 thermometers. And the bulbs of T1 and T2 thermometers are placed in those two holes. Two small holes are constructed in the rod. Two small holes are constructed in the rod, and the bulbs of T1 and T2 thermometers and the bulbs of T1 and T2 thermometers are placed in the holes. Number 6. The distance between the two holes, within brackets simple d, the distance between the two holes within brackets simple d is measured by using a meter rule. The distance between the two holes within brackets simple d is measured by using a meter rule. Who would like if I repeat it? Anybody in the class? Right, look at board there. In this experiment, we should measure this distance between these two holes, right? Please mark the distance between these two holes as simple d, right? If you want, we can use two letters to indicate them as W and Z. So W and Z are the two holes. The distance between W and Z are measured by using a meter rule. So distance between W and Z holes, simple D. Okay, dear? Lamai? Number 7. Am I right, dear? Is it experiment number 7 or 7th step or 6?
7.
It's the 7th step, sir.
It's 7, right? Thank you, Buddha. Thank you very much. Number 7. I think you have named the point WZ and the distance simple D. Number 7, please write. Initially, it can be observed that readings of T1, T2, T3. Initially, it can be observed that the readings of T1, T2, T3 increase with the time. Increase with the time. Increase with the time. Full stop. Number 8. So initially you can observe that initially readings of all the 4 thermometers may be 30 degrees. Initially all the thermometers may read 30 degrees Celsius. But with the time T1 reading of T1 may be increased 40 degree, 50 degree, 60 degree, 70 degree Celsius, like that. T2 reading will also be increased. T3 reading will also be increased, but reading of T4 remains unchanged. Why is that? Reading of T4 remains unchanged. In the examination, they will ask why the reading of T4 remains unchanged. Somebody unmute the mic and tell me the reason.
Because it is the water inlet.
Yeah, because normal water flows through it, flows across it. The water at room temperature flows in that place. So therefore, reading of T4 will be equal to the room temperature. So that will not be changed. But when water flows through the copper tube, heat energy in the rod is absorbed by water. Therefore, reading of T3 will be increased because hot water will flow across the T3. And at the same time, heat energy flows from X2I. So due to that heat energy, rod will be heated. Therefore, reading of T1, T2 increases. Okay, right. I'll again explain. Listen to me carefully. But before that, somebody please read the experimental step 7 here. Somebody unmute the mic and read step 7.
Initially, it can be observed that readings of T1, T2, T3 increase with the time.
Okay, thank you very much. Number 8. After that, I'll again explain. Number 8. After few minutes, we just wait about 10 minutes. 10 to 15 minutes, we wait. After few minutes, the height within bracket simple h. After few minutes, the height simple h. The height within bracket simple h of the constant pressure head. After few minutes, the height within bracket simple h of the constant pressure head is adjusted. The height of the constant pressure head is adjusted until all the thermometers, after few minutes, the height of the constant pressure head is adjusted until all the thermometers read constant different temperatures. Until all the thermometers read constant different temperatures. What does it mean, dear? We sometimes you have to increase the pressure head. If we increase the height h of the pressure head, water will flow to the copper spiral with the larger speed. If we reduce the height simple h, then the flow of water through the copper head will be smaller. So we can increase and decrease the speed of water in the copper spiral, right? By changing the height simple h. Is it clear for all? If we increase
No,
the, is it clear, dear Lamai?
No, sir.
No.
Can you repeat it
This
again?
is a rubber tube. This green color one is a rubber tube. So if we can bend the rubber tube and we can move this water vessel upward. So height is increased mean there will be more potential energy. Therefore, water will flow through the copper tube with a larger velocity. Is it clear or not?
Yes, sir.
Right. So water will flow with a larger velocity if we increase this height. And if we decrease the height, this height simple h, the velocity of water in the copper tube will be small. So we adjust this height until reading of all the thermometers become not same, but they will read different constant temperatures. So that's what I'm going to explain next. So I have used some arrowheads to increase to show you the path followed by water. I have used some arrowheads to show you the path followed by water. Is it clear here? Right. So after 10 or 15 minutes, we change the height simple h until all the 4 thermometers read constant but different temperatures, such as reading of T1 90 degrees Celsius, reading of T2 60 degrees Celsius, reading of T3 35 degrees Celsius, something like that. Can you understand here? T4 may be 25, T3 25, T2 60, T1 90. Readings will not be changed. Different readings but constant, they will not be changed. Is it clear or not?
It's clear, sir.
Right. Put a star point and write. Put a star point and write.
So is it the ninth statement or
A star point here.
Okay, sir.
Okay, it's a star point. Star point and write. Because it's not an experimental step. Star point and write. Once the thermometers read constant different temperatures. Once the thermometers read constant different temperatures. Once the thermometers read constant different temperatures, comma, it is said that once the thermometers read constant different temperatures, comma, it is said that the system has reached to the, it is said that the system has reached to the, use a different color pen and write, once the thermometers read constant temperatures, comma, it is said that the system has reached to the, use a different color pen and write, steady state. The system has reached to the steady state. Once the thermometers read constant different temperatures, comma, it is said that the system has reached to the steady state. This will be asked. And you should know what the steady state is. Am I right? Otherwise, it will just be it will be just 2 words. Steady state means something like this. Steady state means something like this. Listen to me carefully. Right. Let's say we provide, listen to me very carefully, give your maximum attention. Let's say we provide 100 joules to the end X of the rod for 1 second. How much heat energy is given to the end X of the rod there? Tamai?
100 joules for
100 joules within how many seconds, dear?
1 second.
1 second. Let's say that 100 joules of heat energy flows from X to Y, and listen to me very carefully, and only 30 joules of heat energy, only 30 joules of heat energy absorbed by water per second. How much heat energy is given to the rod, Lamai? You have to talk to me. How much heat energy is given to the rod for 1 second?
100
100
joules.
100 joules. How much heat energy is absorbed by water per second?
30 joules per second.
So, what is the difference?
70 joules.
70 joules. So, that 70 joules of heat energy, listen to me carefully. That 70 joules of heat energy is absorbed by the rod. Then what will happen to the temperature of the rod there?
Increase.
Temperature of the rod should be increased. Let me explain again. You must understand the things there. You should not worry about the time taken to complete the lesson because it's a duty of a teacher. I know how to complete the theory within the given time period, and nobody can cover the syllabus earlier than me because I am the fastest teacher, right? So don't worry about the time taken. Now let's start from the very beginning. 100 joules of heat energy is given to the rod for 1 second, right? But 70 joules of heat energy is absorbed by the rod. Only 30 joules of heat energy is given to the water per second. What will happen to the temperature of the rod due to this 70 joules of heat energy? Somebody please tell me.
Decrease.
Increases. Therefore, what will happen to the readings of T1 and T2, dear?
Increase.
Increase. Readings of T1 and T2 increase due to this 70 joules of heat energy. Within the next second, even in the next second, we give another 100 joules of actually steam, not we. Steam gives another 100 joules of heat energy to the end X of the rod. Now, the rod absorbs only 50 joules of heat energy. The rod absorbs only 50 joules of heat energy. So then what will be the amount of heat energy absorbed by water? May I explain again? 100 joules of heat energy is given to the rod for 1 second. 50 joules of heat energy absorbed by the rod itself. And heat energy given to water is, can you tell me the amount?
50 joules.
50 joules. Right, 50-50. Now I'm going to talk about the third second. First second, 100 given, 70 absorbed by the rod, 30 given to water. Second second, we have given 100 joules to heat energy rod. Rod has absorbed 50, 50 is given to water. During the third second, again we give 100 joules of heat energy to the rod. And rod absorb only 20 joules of heat energy. Then what is the amount of heat energy absorbed by water?
80.
80 joules. So next second we use 100 joules of heat energy to the rod. The rod absorb only 10 joules of heat energy. Then what will be the amount of heat energy absorbed by water?
90 joules.
90. Because of this 10 joules of heat energy, what will happen to the temperature of the rod there? Lamai? Because of this 10 joules of heat energy, what will happen to the temperature of the rod?
Increase.
Increases.
Yeah, if heat energy is absorbed by the rod, temperature of the rod will be increased. Therefore, T1 and readings of T1 and T2 will be increased. Now, within the fifth second, we give another 100 joules of heat energy to the rod. Then the rod does not absorb any heat energy. It means amount of heat energy absorbed by the rod is 0 degrees Celsius. Then what will be the amount of heat energy absorbed by water? Somebody unmute the mic and tell me.
100 joules.
100. All the 100 joules of heat energy is completely absorbed by water. Now, Rod has not absorbed any heat energy. All the heat energy just flow through the rod and completely given to water. As the rod has not absorbed any heat energy, will the readings of T1, T2 be increased or not?
They will remain constant, sir.
Very good. Excellent. No heat energy is absorbed by the rod. Therefore, readings of T1, T2 remains unchanged because as no heat energy absorbed mean temperature is not increased. As the temperature of the rod is not increased, reading of T1 and T2 remain unchanged. Is it clear for all, or may I again explain?
Sir, I have a question. May I ask you the question?
Yes, definitely, Buddha. Please ask.
Sir, since at point X, the 100 joules is given by steam, right?
Yes.
So when the water in the copper tube increase, like absorb 100 joules, will the water inside the copper tube turn to steam?
No, dear. The point here is temperature at X is 100 degrees Celsius, but temperature at Y is most probably maybe 50 or 60 degrees Celsius, like that. As the temperature of water at temperature of the end Y is less than 100 degrees Celsius, temperature of water in the copper tube will be less than 100 degrees Celsius. It's mostly about 40 or 50. Water in the copper tube will not be converted into steam. Is it clear, Buddha?
Yes, sir. Thank you.
Okay, right. My question is, okay, my question is, we have given 100 joules. All the 100 joule is absorbed by water. Rod has not absorbed heat energy. Therefore, readings will not of T1, T2 will not be increased. During the next second, we give another 100 joules of heat energy. And amount of heat energy absorbed by the rod is 0. Then what is the amount of heat energy absorbed by water? Let me repeat. 100 joules of heat energy. During the next second, we have given 100 joules of heat energy to the end X of the rod for 1 second. All the 100, rod has not absorbed any heat energy. It just transfer the heat energy from X to Y. So, if so, what will be the amount of heat energy absorbed by water?
100 joules.
100 joules of heat energy. So, this is what we called as steady state. At the steady state, heat energy just flow through the rod, but rod does not absorb any heat energy. Therefore, readings of T1, T2 will not be increased. All the heat energy is completely given to water, right? And we have adjusted the speed of water. So even the reading of T3 will remains unchanged, right? Put another star point. This is not the point 9, but the next star point. Next star point. At the steady state, all the heat energy flows through the rod. At the steady state, all the heat energy flows through the rod, is completely absorbed by water. At the steady state, all the heat energy flows through the rod, is completely absorbed by water. Is completely absorbed by water. Full stop. No heat energy is absorbed by the rod. No heat energy is absorbed by the rod. Therefore, no heat energy is absorbed by the rod. Therefore, the temperature of the rod is not increased. The temperature of the rod is not increased. Hence, temperature of the rod is not increased. Full stop. Hence, the reading of T1 and T2 remain unchanged. Hence, the reading of T1 and T2 remain unchanged. Hence, the reading of T1 and T2 remain unchanged. Within brackets, constant. Hence, the reading of T1 and T2 remain unchanged. Within brackets, constant. Right. Somebody unmute the mic and read that star point. We just won't write 2 more sentences, then the things will be completed. Somebody please read that star point there.
At the steady state, all the heat energy flows through the rod is completely absorbed by the water. No heat energy is absorbed by the rod. Therefore, the temperature of the rod is not increased. Hence, reading of T1 and T2 remain unchanged. Constant.
Thank you. Thank you very much. Who would like to listen to that point once again? Who wants to listen to it once again? Anybody in the class? Right. Experimental step number 9. Experimental step number 9. Readings of all the thermometers are noted at the steady state. Readings of all the thermometers are noted at the steady state. Readings of all the thermometers are noted at the steady state. Number 10. Number 10. At the steady state, comma, a stopwatch is started. At the steady state, a stopwatch is started, and the water flows through the copper tube, and water flows through the copper tube, is collected into a measuring cylinder for few minutes. At the steady state, a stopwatch is started and water flows through the copper tube, is collected for few minutes. At the steady state, a stopwatch is started and water flows through the copper tube, is collected for few minutes. Right, so that's the end of the practical. Right, so please write the next subheading saying calculations. The next subheading, calculations. Right, so I'll do the calculation next week, and I'll discuss a past paper question also next week. So this is the 4th practical. So there will only be 6 more practicals to be completed. Right, and I wish to start electricity lesson also. I'll discuss with you using WhatsApp. Okay, is it enough for today, dear? Do you have any other doubt, or may I stop the class? Can somebody read the step 8, dear? Somebody please read step 8 before we stop the class.
After a few minutes, the height edge of the constant temperature head is adjusted until all the thermometers read constant different temperatures.
Right, thank you very much, dear. And if it is possible, somebody please take photos of the note and send to the WhatsApp groups, dear, or send directly to the class admin. Then we can share the notes with others, and that will be a big help. So that's enough for today. See you next week. Good night. Good luck. Bye.
Thank you, sir. Good night.
Thank you. God bless you, sir.
Thank you, sir.
Okay, I just want to record the statements that we have discussed last week for this practical. So that's why I asked. Once we all the statements that we discussed last week, we can speak all the statements here.
Practical number 3, determination of specific latent heat of vaporization. Step 1, the mass of an empty calorimeter with a stirrer is measured by using a triple beam measure. Step 2, more than 90% of the calorie is filled with cold water, which is at few degrees below the room temperature. Step 3, the mass of the calorimeter with the stirrer and cool water is measured by a triple beam balance. Step 4, the initial temperature of water in the calorimeter is measured. Step 5, steam is passed onto the surface of the water in the calorimeter and water is well stirred. Step 6, the steam is sent into the water until the temperature of the reader few degrees greater than the room temperature. Step 7, the following experiment procedure is used to find the final temperature. The steam is not further provided to the water and water is well stirred. The maximum temperature of the achieved by the water is measured as the final temperature. Step 8, the steam which is sent to the water is converted to liquid water and deposited in the calorimeter. Therefore, the mass of the calorimeter is increased. Step 9, finally, the mass of the calorimeter with the stirrer water and condensed steam is measured.
How many steps have we written here? Is that all we have written?
Only 9 steps, sir.
Right. We have written up to 9 steps. Right. So we have written these 9 steps. So we have read the 9 steps again because we want to do some calculation as well as we want to do a past paper question. Right. So we have taken 3 mass readings, M1, M2, and M3. And we have obtained 2 temperature readings, theta 1 degree Celsius and theta 2 degree Celsius. So today we should start the calculations, right? I just want to revise the things that we have written before we go for the calculations and the past paper questions, right? So I use my normal whiteboard and I do the calculations. Look at board here. Right, I think you are able to see the board clearly. Right, so write the heading as write the subheading as calculations. Calculations. Right. Okay. Under that, please write first statement. The mass of the empty first statement. We are going to write some statements. The mass of the empty calorimeter. The mass of the empty calorimeter with its stirrer. The mass of the empty calorimeter with its stirrer equals simple M1. Mass of the empty calorimeter with the stirrer equals simple M1. Mass of the empty calorimeter with the stirrer equals simple M1. M1. Next statement. Next statement. Specific heat capacity of the material of the calorimeter. Specific heat capacity of the material of the calorimeter. Specific heat capacity of the material of the calorimeter equals C1. M1 is its mass, C1 is the specific heat capacity of the material of the calorimeter. For example, if the calorimeter is made of copper, C1 is the specific heat capacity of copper. Got it? Like that. Next statement. The initial temperature of the calorimeter and stirrer. The initial temperature of the calorimeter and the stirrer. The initial temperature of the calorimeter and the stirrer equals what is the initial temperature of calorimeter and stirrer? As I remember, theta 1. Yes, it is theta 1 degree Celsius. The initial temperature of the calorimeter and the stirrer equals theta 1 degree Celsius. Next equation. The final temperature of the calorimeter and the stirrer. The final temperature of the calorimeter and the stirrer. The final temperature of the calorimeter and the stirrer equals theta 2 degree Celsius. Theta 2 degree Celsius. Okay, dear. Therefore, the increase in temperature, of the calorimeter and the stirrer. Therefore, the increase in temperature of the stirrer and the calorimeter. Somebody unmute the mic and tell me the increase in temperature of the calorimeter and the stirrer. Somebody unmute the mic and tell me. Quick.
Theta 2 minus theta 1.
Yes, very good. Final temperature is theta 2. Temperature, we start the practical with cool water, right? If you read the statements properly, all the experimental steps, we start the practical with cool water. Therefore, initial temperature of calorimeter, stirrer and water very low, less than normal room temperature. So, with the time, temperature increases, right? So, theta 2 is bigger than theta 1. Therefore, the final increase in temperature will be theta 2 minus theta 1 degree Celsius. Please write the increase in temperature equals theta 2 minus theta 1. Okay, dear? Lamai? Hello, is it okay? Right, leave a line and write. Leave a line and write. Therefore, next statement. Therefore, the amount of heat energy. Therefore, the amount of heat energy absorbed. The amount of heat energy absorbed by. The amount of heat energy absorbed by the calorimeter and the stirrer. Therefore, the amount of heat energy absorbed by the calorimeter and the stirrer. Therefore, the amount of heat energy absorbed by the calorimeter and the stirrer. So, amount of heat energy absorbed by anything can be found by the equation MC theta. MC theta. So, here mass of the calorimeter with the stirrer is M1, specific heat capacity C1, the temperature difference is theta 2 minus theta 1. Therefore, amount of heat energy absorbed by the calorimeter and the stirrer is given by M1 into, if you want to erase the bracket, M1 into C1 into theta 2 minus theta 1. The amount of heat energy absorbed by calorimeter and the stirrer is given by M1 into C1 into theta 2 minus theta 1. Complete there. Please write them all. Write them all. Right, now somebody unmute the mic and read all the statements that we have written so far. Starting from M1, somebody please read all the statements. That will be a big help for other students. There may be some students who are not able to write the notes. So I always ask you to practice this thing. What is it? You must help others, then only God will help you back. So as a help for the student who are not able to write the notes, so please read, somebody unmute the mic and read all the statements quickly.
The mass of the empty calorimeter with the stirrer is M1. Specific heat capacity of the material of the calorimeter is C1. The initial temperature of the calorimeter and the stirrer equals theta 1 degree Celsius. The final temperature of the calorimeter and the stirrer equals theta 2 degrees Celsius. Therefore, increase in the temperature of the stirrer and the calorimeter equals theta 2 minus theta 1. Therefore, the amount of heat energy absorbed by the calorimeter and the stirrer equals M1 into T1 into theta 2 minus theta 1.
Okay, only these statements that we have written today. Would you please take a photo? Please take a photo of the note that we have written today and send to the WhatsApp group today. That will be helpful for other students. Right. While you are doing it, I would like to listen to voice of one more student. Can another student read all the statements that we have written today? One more student, please read the statements that we have written today. Somebody, please, quick.
The mass of the empty calorimeter with its stirrer equals M1. Specific heat capacity of the material of the calorimeter equals C1. The initial temperature of the calorimeter and the stirrer equals theta 1 degrees Celsius. The final temperature of the calorimeter and the stirrer equals theta 2 degrees Celsius. Therefore, the increasing temperature of the calorimeter and the stirrer equals theta 2 minus theta 1 degrees Celsius. Amount of heat energy absorbed by the calorimeter and the stirrer equals M1 into C1 into theta 2 minus theta 1 degrees Celsius.
Right. Thank you very much. Thank you very much. Two students helped us. I'm really thankful for both students. Right now, what did we do next year? First, we take only the calorimeter and its stirrer. After that, more than 90% of the calorimeter was filled with cool water. Then we measured the mass of the calorimeter with the stirrer and the cool water. So please try the next statement, but we have to start again talking about it. Actually, we are going right about M2, but let's start again with M1, then only you can understand it. So please try the next statement. The mass of the empty calorimeter with the stirrer. The mass of the empty calorimeter with the stirrer. the mass of the empty calorimeter with the stirrer equals simple M1. Mass of the empty calorimeter with the stirrer equals simple M1. The mass of the empty calorimeter with the stirrer equals simple M1. Next statement. The mass of the calorimeter with the stirrer and cool water. The mass of the calorimeter, next statement. The mass of the calorimeter with the stirrer and cool water. Mass of the calorimeter with the stirrer and cool water equals simple M2. Simple M2. Okay. Next statement. Therefore, the mass of cool water. Therefore, the mass of cool water. Therefore, the mass of cool water. Right. Somebody unmute the mic and tell me what should be the mass of cool water.
M2 minus M1.
Sorry, dear.
M2 minus M1.
M2 minus M1. The mass of cool water equals M2 minus M1. Very good. Mass of only the calorimeter and stirrer M1. After water is placed in the calorimeter, the mass is increased from M1 to M2. Therefore, mass of water should be M2 minus M1. Next statement. The specific heat capacity of water. The specific heat capacity of water equals, normally we use CW. Please write. Specific heat capacity of water is CW. Specific heat capacity of water equals CW. CW. Next statement. Next statement. The initial temperature of water. The initial temperature of water. The initial temperature of water equals theta 1 degree Celsius. I have written the units also. Theta 1 degree Celsius. The initial temperature of water equals theta 1 degree Celsius. Right? Next statement. The final temperature of water. The final temperature of water. The final temperature of water equals theta 2 degree Celsius. Theta 2 degree Celsius. The final temperature of water equals theta 2 degree Celsius. Right. Next equation. Therefore, the increase in temperature of water. Therefore, the increase in temperature of water. Therefore, the increase in temperature of water. Somebody unmute the mic and tell me the increase in temperature of water. Somebody?
Theta 2 minus theta 1.
Theta 2 minus theta 1. Very good. Theta 2 minus theta 1 degree Celsius. Right. Somebody please unmute the mic and read all these statements quickly, dear. Somebody quickly unmute the mic and read all the statements.
The mass of the empty calorimeter with the stirrer equals M1. The mass of the calorimeter and the stirrer with cool water equals M2. Therefore, the mass of cool water equals M2 minus M1. The specific heat capacity of water equals Cw. The initial temperature of water equals theta 1 degrees Celsius. The final temperature of water equals theta 2 degrees Celsius. Therefore, the increase in temperature of water equals theta 2 minus theta 1 degrees Celsius.
Thank you, dear. Thank you very much. Right. Next statement. Next statement in the same series. Next statement. Therefore, the amount of heat energy absorbed by water. Therefore, the amount of heat energy absorbed by water. The amount of heat energy absorbed by water can also be found by the same equation mc theta. The amount of heat energy absorbed by water equals m, mass of water, m2 minus m1, mass of water, m2 minus m1, into c, specific heat capacity of water, cw, into the increase in temperature, that is theta 2 minus theta 1. Right? So let me take this as my second equation. Write it here. I'll take it as the second equation. Write it here. So what's the final statement? Therefore, the amount of heat energy absorbed by water. Therefore, the amount of heat energy absorbed by water equals mc theta. mc theta. M is m2 minus m1, c is Cw, theta is the temperature difference or increase in temperature, that is theta 2 minus theta 1. Complete there. Right, now we have discussed about the empty calorimeter and its stirrer, and now we have discussed about the water in it. So what are things we placed in the calorimeter? Calorimeter, stirrer, water in it. Right. Now, if you in this practical, we send steam. We send steam into this. Right? That steam, when the steam touches the water surface, steam gives heat energy out, and steam converted into liquid water, and that liquid water deposited in the calorimeter. So what other things will happen here? We have sent steam into the surface of water. We do not send steam inside the calorimeter. I'll explain the reason. We send steam onto the surface of water. Once the steam touches the water surface, heat energy is given out. Then steam converted into liquid water. Right? That liquid water deposited in the calorimeter. And the heat energy given out by steam is absorbed by cool water in the calorimeter, stirrer in the calorimeter, and the calorimeter. Steam gives heat energy out. That heat energy is absorbed by calorimeter, stirrer, and cool water. Therefore, temperature of calorimeter increases, temperature of stirrer increases, temperature of cool water increases. That's why temperature increases from theta 1 to theta 2. Right? And mass of the system will be increased because of these deposited steam. As steam deposited in the calorimeter, steam converted into water, and that water deposited in the calorimeter. Therefore, mass of the calorimeter will be increased from M2 to M3. M2 to M3. Right. So I just revised the practical, right? So please try the next statement. We have discussed all those things earlier, right? So please try the next statement. We should start with M2 because now we are going to go to M3. We start with N2 because we are going to go to M3. Please write first statement. The mass of the calorimeter with the stirrer and cool water. Mass of the calorimeter with the stirrer and cool water. The mass of the calorimeter with the stirrer and cool water equals N2. Mass of the calorimeter with the stirrer equals mass of the calorimeter with stirrer and cool water equals N2. Next equation. The mass of the calorimeter with the stirrer, water and condensed steam. The mass of calorimeter with the stirrer, water and condensed steam. This steam, I'm talking about this steam, condensed steam equals M3. Right? Next statement. Therefore, the mass of condensed steam. Therefore, the mass of condensed steam. Therefore, the mass of condensed steam equals. Somebody unmute the mic and tell me. What is the mass of condensed steam here? Lamai? What is the mass of condensed?
M3 minus M2.
Again?
M3 minus M2.
M3 minus M2. Very good. The mass of condensed steam equals M3 minus M2. Please write. The mass of condensed steam equals M3 minus M2. M3 minus M2. Right. Next equation. Specific latent heat of vaporization of water. Specific latent heat of vaporization of water equals, let me use the term, we can use any term, specific latent heat of vaporization of water, let me use capital L, or if you want you can use simple L. Specific latent heat of vaporization of water equals capital L. Right. Now somebody unmute the mic and tell me the definition of specific latent heat of vaporization. Somebody unmute the mic and tell me the definition of specific latent heat of vaporization.
The amount of heat energy needed to convert a unit mass of liquid completely into its vapor at its boiling point is defined as the specific latent heat of vaporization of that liquid.
Right, thank you. It is the amount of heat energy needed for a unit mass of a liquid. It is the amount of heat energy needed for a unit mass of a liquid to be completely converted into its vapor at its boiling point. Everybody, what is specific latent heat of vaporization of a liquid here? What is specific latent heat of vaporization of a liquid? It is the amount of heat energy needed for a unit mass of a liquid to be completely converted into its vapor at its boiling point. Clear? For example, boiling point of water is 100 degrees Celsius, and you know what the boiling is. A unit mass means 1 kilogram. 1 kilogram. So the amount of heat energy needed for 1 kilogram of a liquid to be completely converted into 1 kilogram of vapor at the boiling point is said to be specific latent heat of vaporization. Now my question is this here. Listen to me. So let's say there is a liquid. There is a liquid of 1 kilogram. Let's say boiling point is 300 degrees Celsius. We provide heat energy. We provide 1000 joules of heat energy. Then this liquid is converted into its vapor. And you should know that when we provide heat energy, to a liquid at its boiling point, the temperature not change. That's one of the magical things that can be observed. Normally, when we provide heat energy to a liquid, temperature increases. But once the liquid reaches to its boiling point, even we provide heat energy, the temperature will not be increased. The temperature is not increased any further. But liquid converted into its vapor. So once you provide 1000 joules of heat energy, let's say we get 1 kilogram of vapor at the temperature of 300 degrees Celsius. At the temperature of 300 degrees Celsius. That's why we call this constant temperature is called the boiling point. This constant temperature is called the boiling point. There is a definition, but this is one of the meanings of the boiling point. Right. My question is, once we give 1000 joules of heat energy to this 1 kilogram of liquid, it is converted into vapor. My question is, what will happen if the vapor converts into liquid? How much of heat energy will be given out when this vapor converted into liquid at the same boiling point? Can you understand my question? Right. Somebody unmute the mic and tell me how much heat energy, the amount of heat energy given out by this vapor when it is converted into its liquid. Right here.
1 kilojoule.
1 kilojoule. It means how many joules here?
1000.
1000 joules. So this is what happened here. So this is correct. Very good. So if we give 1000 joules to the liquid, when it is at the boiling point, liquid converted into vapor. If we give 1000 joules of heat energy to 1 kilogram of the liquid, when it is at the boiling point, liquid converted into vapor. Then that 1000 joules of heat energy absorbed by the vapor is given out when the vapor is converted into liquid. Can you understand it? If we give 1000 joules, liquid will be vapor. If we allow vapor to be converted into liquid, that 1000, here it absorbed 1000 joules, that absorbed 1000 joules of heat energy is given out. Okay, dear? So simple, right? So this 1000 joule is said to be the specific latent heat of vaporization of liquid. This 1000 as well as this 1000. Can you understand it? Any of 1000 joules can be said to be the specific latent heat of vaporization. Right. So there was M2 minus M1 mass of steam, which is at 100 degrees Celsius. That steam converted into, M3 minus M2. There was M3 minus M2 kilograms of steam at 100 degrees Celsius. Temperature of steam is 100 degrees Celsius, right? That much of steam converted into liquid. If 1 kilogram of steam converted into water, it will give L joules of heat energy out. If 1 kilogram of steam converted into water, it will give capital L joules of heat energy output. Here, M3 minus M2 kilograms of steam is converted into water. Therefore, how much heat energy will be given out by this much of steam? Somebody unmute the mic and give me the answer. I want the answer with the symbols. Lamai?
M3 minus M2 multiplied by L.
Very good. M3 minus M2. I didn't hear you the rest.
Multiplied by L.
Multiplied by L. L is the amount of heat energy given out by 1 kilogram. Here we have M3 minus M2 number of kilogram of steam. Therefore, amount of heat energy given out by this much of kilogram is equal to M3 minus M2 into L. Would like if I explain it again? Anybody in the class? If you want to explain it again, just raise your hand up, then I can explain. Okay, right. Now, sign up, please tell me the definition of capital L. Unmute the mic and read the definition of capital L. Sign up. Okay, Nilfa, would you please read the definition of capital L? Then only I can help you. Because if you do not have that clear note, if you absent that day, you can't understand this. Yes. But if you have listened to when I was explaining this, you may have understood it now. But okay, in your own words, or according to the correct definition, please define capital L. Nilfa, or the student who, some of the students asked me to explain this again. One of those students, please give me the definition of capital L. Then only I can help you. Right. So they do not have that theory note. So please read that theory note and ask me next week, then I'll explain, right? So if you want to explain this equation again, you must tell me the definition of capital L. That is very much reasonable, right? If you do not know what the capital L, then you cannot understand. So the best thing is find the note where we have written this L and give me the definition, then I will help you. Okay, dear? That's much fair. Otherwise, to explain this capital L, I will take more than 1 hour. Right. So please try the next statement. Therefore, next statement. Therefore, the amount of heat energy given out by steam. Therefore, the amount of heat energy given out by steam. Therefore, the amount of heat energy given out by steam, when it is converted into liquid water at the boiling point. Therefore, the amount of heat energy given out by steam when it is converted into liquid water at the boiling point. When it is converted into liquid water at the boiling point equals capital M into capital L. Capital M into capital L. Right? So if capital M number of kilograms, if capital M number of kilogram converted into liquid water, ml amount of heat energy will be given out. If only 1 kilogram of steam converted into liquid water, it will give L joules of heat energy out. For 1 kilogram steam will give L joules of heat energy. Then M kilograms will give ml joules of heat energy. That's it. Very simple, right? So, but here, listen to me carefully. But here, M, mass of steam. Here, mass of steam is M3 minus M2. L is the thing that we are going to find. So mark this as the third equation. Please mark this as the third equation. Write them there. Okay, I think you have written all. Somebody please, there is a request from a student. Somebody please read these statements here. M2, M3, M3 minus M2L, and these three statements here. Somebody please quickly unmute the mic and read the statements.
The mass of the calorimeter with the stirrer and the cool water equals M2. The mass of the calorimeter with the stirrer, water, and the condensed steam equals M3. Therefore, the mass of the condensed steam equals M3 minus M2. Specific latent heat of vaporization of the water equals L. Therefore, the amount of heat energy given out by the steam when it is converted into liquid water at the boiling point equals capital M into L equals to M.
Right. Final statement was the amount of heat energy given out by steam when it is converted into liquid water. The amount of heat energy given out by steam when it is converted into liquid water. Right. Look at board B. Look at board carefully. There was some steam. There is some steam. There is some steam. Mass of this steam is M3 minus M2. Mass of this steam is M3 minus M2. Right. The temperature of steam is 100 degrees Celsius. So this M3 minus M2, I was indicated this as capital M. The term capital M indicates this M3 minus M2 amount of steam. This M3 minus M2 amount of steam indicated by capital M. The first thing is the steam converted into liquid water. The steam converted into liquid water, right? But temperature remains unchanged. The temperature remains unchanged. The same capital M amount of steam converted into liquid water at 100 degrees Celsius. The water which is created by this steam, is said to be condensed steam. This is called said to be condensed steam. Condensed steam. Right? This condensed steam you should understand that this steam is kept, this water at 100 degrees Celsius, which is known as condensed steam. Right? This condensed steam collected in the calorimeter. The final temperature of the calorimeter and water, theta 2 degrees Celsius. Therefore, temperature of this water reduces to theta 2 degrees Celsius, because finally the final temperature of everything, is theta 2 degrees Celsius. Therefore, temperature of this further reduced, and to theta 2 degrees Celsius. So this is the same water of mass capital M, which is equal to M3 minus M2 kilogram. Right. Before we go to next statements, draw this figure here. Please draw this figure. I need this figure to explain the rest of the things. I need this equation. So please draw this figure here. Draw this figure quick. Right. I think time is enough. I think time is enough to write these things. So please try it. Continue the note. Star point and write. Star point and write. The condensed water, the condensed steam, sorry, the condensed steam, the condensed steam, the condensed steam is at 100 degrees Celsius temperature. The condensed steam is at 100 degrees Celsius temperature. The condensed steam is at 100 degrees Celsius temperature. Full stop. The temperature of that condensed steam, the temperature of that condensed steam is reduced to theta 2 degrees Celsius. The temperature of that steam is reduced to theta 2 degrees Celsius. The temperature of condensed steam is reduced to theta 2 degrees Celsius. Full stop. Heat energy is given out during that process. Heat energy is given out during that process. Heat energy is given out during that process. Right. Somebody unmute the mic and read that star point here. Somebody unmute the mic and read that star point.
The condensed steam is at 100 degrees Celsius temperature. The temperature of that condensed steam is reduced to theta 2 degrees Celsius. Heat energy is given out during that process.
Very good. Thank you, Ria. Right. Leave a line and write our final statement. Leave a line and write the final statement. Therefore, the amount of heat energy given out by condensed steam, therefore the amount of heat energy given out by condensed steam, when its temperature is reduced from 100 degrees Celsius to theta 2 degrees Celsius. The amount of heat energy given out by condensed steam when its temperature is reduced from 100 degrees Celsius to theta 2 degrees Celsius. The amount of heat energy given out by condensed steam when its temperature is reduced from 100 degrees Celsius to theta 2 degrees Celsius. The amount of heat energy given out by condensed steam when its temperature is reduced from 100 degrees Celsius to theta 2 degrees Celsius equals, look at board, equals MC theta. Equals MC theta. This is the equation that we use. Mass of steam is M3 minus M2. Mass of steam, mass of condensed steam, mass of the water. M3 minus M2. Specific heat capacity of water is TW. Temperature reduces from 100 degrees Celsius to θ2. Temperature reduces from 100 degrees Celsius to θ2. Therefore, decrease in temperature is 100 minus θ2. 100 minus θ2. So, let me mark this as the fourth equation. Let me mark this as the fourth equation. Write it here. Please write it. Right. Finally, you should understand that when steam converted into liquid water at 100 degrees Celsius, when steam converted into liquid water at 100 degrees Celsius, and when the temperature of this water reduces from 100 to θ2 degrees Celsius, heat energy is given out. In this process, heat is given out. During this process, heat is given out. That heat energy is absorbed by the calorimeter, stirrer, and cool water which was kept in the calorimeter. Got it? Star point and write. During the above two processes, heat energy is given out. Star point and write. During the above two process, heat energy is given out. Heat energy is given out. Heat energy is given out. Full stop. That heat energy is absorbed by the calorimeter, stirrer, and cool water. During the above two process, heat energy is given out. Full stop. That heat energy is absorbed by the calorimeter, stirrer, and cool water. Right. So leave a line and write. This equation. Just look at board. Leave a line and write this equation. Therefore, the amount of heat energy, given out Just look at board, don't write. Just look at board, don't write. The amount of heat energy given out by steam and condensed steam. The amount of heat energy given out by steam and condensed steam. Condensed steam means liquid water at 100 degrees Celsius. Condensed steam means liquid water at 100 degrees Celsius. That liquid water was created by steam, right? Equals, right? They give heat energy. Steam gives heat energy out. That heat energy was absorbed by, look at what? That heat energy is absorbed by amount of heat energy absorbed. Amount of heat energy absorbed by calorimeter, stirrer, and I have already explained stirrer and cool water. Stirrer and cool water. Write them there quick. Amount of heat energy given out by steam and condensed steam equals the amount of heat energy absorbed by calorimeter, stirrer and cool water. Stirrer and cool water. Cool water. Okay, dear. I have written 1 and 3 equation this side because I want to erase, right? I have written the 2 equation that side so I can erase it. Right, so if you check the 4 equations that we have written so far, it must be clear that, right? It must be clear that the amount of heat energy given out, given out by steam and condensed steam is given by the equations 3 and 4. Heat energy given out by steam, equation number 3. Heat energy given out by condensed steam, equation number 4. So the amount of heat energy given out by steam and condensed steam given by equation number 3 and equation number 4. The amount of heat energy absorbed by calorimeter and stirrer given by equation number 1 heat energy absorbed by cool water is given by which number? 2. So this should be the second step. Amount of heat energy given out by steam, amount of heat energy given out by condensed steam, amount of heat energy absorbed by calorimeter and stirrer, and the amount of heat energy absorbed by what? Cool water is given by the second equation. So third equation, by looking at here, I can write it. The third equation is M3 minus M2 times capital L plus fourth equation here, that is M3 minus M2 times ZW into 100 minus theta 2 equals first equation. First equation is here M1 Z1 plus, sorry, M1 into Z1, M1 into Z1 into M1 into Z1 into theta 2 minus theta 1 plus M2, second equation, M2 minus M1 into ZW into theta 2 minus theta 1. Right, so I have written all the summation of these equations, right? Complete the note here. Write them, and we are going to subject this capital L. But you write them here quick.
Excuse me, sir.
Right, shall we give a try to subject capital L here? Let me give a try to subject capital L. Look at board. I don't do anything to this term. I just write M3 minus M2 times capital L equals, I'm going to take this term to this side. That's what I'm going to do. I'm going to take this term to the other side. So if I consider here M1 into C1 into theta 2 minus theta 1. Again, I have M2 minus M1 into CW. Again, theta 2 minus theta 1 is there. So therefore, I take theta 2 minus, look at board carefully. Therefore, I take theta 2 minus theta 1 term out from a bracket. Okay, I open a bracket and take theta 2 minus theta 1 from these two terms. If I take theta 2, theta 1, theta 2 minus theta 1 out from this bracket, the remaining terms will be M1 C1 plus M2 minus M1, M2 minus M1 into CW. Can you understand that step here? Can you understand that step? I have taken theta 2 minus theta 1 and this theta 2 minus theta 1 terms from this. Is it clear for all or not? Is it clear for all here? No doubts. Right, then I'll take this one, this positive term goes to the other side as a negative term. That is M3 minus M2 into CW into 100 minus theta 2. Positive something goes to the other side as negative something. Got it? Now you see, are there any other common terms here? Theta 2 minus theta 1 and no any other common terms. Now simply, I'll take this M3 minus M2. I'll take this M3 minus M2 to this side by cross multiplication. Then L can be subjected. Then L is subjected as all of these things divided by M3 minus M2. All the things divided by M3 minus M2. So this is how we subject capital L. Capital L is specific latent heat of vaporization of water. That's what we wanted to find. Complete it here, quick. Write them. So I erased the board and continue, right? So I asked, I just wanted to know whether you are okay with this, right? So that's why I asked some questions. So let's erase and continue. Right. මම මතක ගිය සතියේ අපි 23 class එකේ හරි දැන් මේ ටියුෂන් එකේ මේ පන්ති වල ළමයි ගොඩක් වැඩි කරගන්න කියලා. ළමයි සංඛ්‍යාව වැඩි කරගන්න ගුරුවරයෙක් වෙන්න නෙමෙයි සල්ලිකාරයෙක් වෙන්න සල්ලි හොයන්න හිතාන බලන්න කියලා ඉන්නවා. මොනවා කරන්නද? සල්ලි හොයන්න ඉගෙන ගන්න සෙට් එකක් ඉන්නවා උගන්වන්නේ. ඒගොල්ලෝ ඉතින් ඕනම කැත වැඩක් කරනවා. දැන් අපේ 23 batch එක තිබ්බා ගිය සතියේ. 23 එකේ class එක classes දෙකක් මම free කරගෙන යන්නේ. මොකද මම දන්නවා සමහර parents වලට සල්ලි නැහැ කියලා. දෙමව්පියන්ගේ දුක දන්නවා. ඒ හින්දා තාමත් සමහර classes යන්නේ free සල්ලි ගන්න නැතුව යන classes තියෙනවා. ඉතින් ඔකේ link එක හැමෝටම දෙනවා ඕන කෙනෙකුට සම්බන්ධලා ඉගෙන ගන්න කියලා. ඉතින් මේ සතියේ මේ සතිය අඟහරුවාදා class එකට එක්කෙනෙක් සම්බන්ධ වෙලා අර Zoom chat එකේ මම හැමෝටම message කරන්න ඉඩ දීලා තියෙනවා. ඒ කියන්නේ note මොකක් හරි ප්‍රශ්නයක් තිබ්බොත් chat එකට message එකක් දාන්න පුළුවන්. මේක තේරුන්නේ නැහැ මොකද කරන්නේ? එහෙම නැත්නම් note එක ලියා ගන්න බැරි වුණා. මේක මොකද කරන්නේ කියලා අහන්න chance එක දීලා තියෙනවා. ඒක misuse කරලා ළමයින්ට හොරෙන් message දාලා මට ඔයාගේ number එක එවන්න. මට ඔයත් එක ටිකක් කතා කරන්න ඕන. මාත් ෆිසික්ස් සර් කෙනෙක් තමයි. ලැජ්ජ නැද්ද අප්පා? ලැජ්ජ නැද්ද? එහෙම ළමයිට message දාලා අහලා ඊළඟට තව ළමයෙක්ට කියලා මට ඔයාගේ මූණ බලන්න හරි ආසයි. කැම්මේ ගොන් කරලා මූණ පෙන්නන්න කියලා. ඉතින් Zoom chat එක දීලා තියෙන්නේ මේ වගේ පිස්සන්ට නෙමෙයි. මට හිතන්න බැරි මේ වගේ අය ගුරුවරු වුණොත් මොකද වෙන්නේ කියලා. දැන් ගුරුවරු වෙන්න ළමයි හොයන ක්‍රමනේ ඔය. ඊළඟට කොහොමද ළමයි ටිකක් වෙලා group එකක් හදලා අර මං කරනවා වගේම admin කෙනෙකුත් පත් කරගෙන හරිද? දැන් class එකක් පටන් ගන්න කියලා දැන් ඉතින් වැඩි සෙට් වෙලා ළමයි 200ක් විතරත් වැඩි දැන් ওই WhatsApp group එකේ ඉන්නවා. කොහොම හරි මන් දන්නේ අපේ ළමෙක් තමයි අපේ ළමෙක් හරි කවුරු හරි ළමෙක් සර්ට අර සර්ට මැසේජ් එකක් කරලා සර් ඇඩ්මින්ට ඇඳුමක් අරන් දෙන්න කියලා. ක්ලාස් එකේ කෝඩිනේටර් හරි ඇඩ්මින් හරි කියන කෙනාට නේ ඔයාලගොල්ලෝ මැසේජ් ගන්න Zoom link එක ගන්න ටියුට්ස් අහන්න ක්ලාස් ෆීස් ගැන කියන්න අර Zoom chat එකේ ඔයගොල්ලෝ මේ WhatsApp එකේ මැසේජ් ගන්න ක්ලාස් ඇඩ්මින්ට එහෙම නැත්නම් ක්ලාස් කෝඩිනේටර් කවුරු හරි කෙනෙක් මැසේජ් එකක් දාලා ක්ලාස් කෝඩිනේටර් ඇඳුමක් අරන් දෙන්න කියලා. මම බැලුවා මොකද කියලා බැලින්නම් මේ ඒ සර් කියන කෙනා මම දන්නේ සර් කියන තරම් සුදුසුද කියලා ඒ වගේ මිනිස්සෙක්. අර කෝඩිනේටර් කියන කෙනා ඇත්තටම මේ ඇඳුමක් ඇඳලා නෑ වගේ මට නම් පේන්නේ. පොඩි රෙදි කෑලි ටිකක් එකේ මම දැක්කා තියෙනවා. ඇඳුමක් ඇඳලා නෑ වගේ නේකඩ් වගේ. ඉතින් එහෙම මේ ගෑනු ළමයිගේ නේකඩ් එක පෙන්නලා මගේ බලන්න මගේ ඇඩ්මින් හරිම නේකඩ් කියලා එහෙමද ළමයි ඉන්න ගන්නේ අප්පා පන්ති වලට. ඊයා. මං හිතන්නේ අපේ පිරිමි ළමයි ඒ වගේ දේවල් බලාගෙන යනවා කියලා. ගුරුවරු හරි කවුරු හරි මන් දන්නේ කවුරු හරි කොහොමද යවලා සර්ට උකට යකා නැගලා සර්ව හතර වටේට මැසේජ් කරලා ළමයිට බැනලා ඒකයි මටත් ආරංචි උනේ සර් කියන්න හොඳ නෑ වගේ මිනිහෙක් හරි මට වගේ මූණ බලන්න ආසයි කියලා මගේ ක්ලාස් එකේ ලින්ක් එක දැම්මම ජොයින් වෙලා මේ ඉන්න ගෑල්ලාට මැසේජ් දාලා මට වගේ මූණ බලන්න ආසයි අනේ වගේ ඔය පොඩ්ඩක් කැම්මේ කොන් කරලා පෙන්නන්නකෝ මේ Zoom එකේ ක්ලාස් එක යන ගමන් දැන් මම ක්ලාස් එකේදී කැම්මේ කොන් කරොත් මටත් ඒ ළමයාගේ මූණ පිළිගිනි පන්තියේ සියලු දෙනාට පිළිගිනි screenshots තියෙනවා මේ මැසේජ් වල. ඔය ඉතින් ප්‍රසිද්ධ කරන්න හොඳ නෑ. මොකද අනවශ්‍ය දේවල් ඉතින් ඒවා පහත්. ඕගොල්ලෝ මම මේ කතාව කියමු මුත් මේ ඕගොල්ලෝ යම් දවසක ගුරුවරයෙක් වෙන්න හිතනවා නම් ඒ වගේ ක්‍රම පාවිච්චි කරන්න එපා. ඔයාට උගන්වන්න හිතනොත් ළමයි දෙන්නෙක් නම් පන්තිරෙන් ඒකට උගන්වන්න. කිසි ප්‍රශ්නයක් නෑ. දැන් මම ඔයගොල්ලන්ට කියලා දෙනවා මම ගම්පහ පන්ති පටන් ගන්නකොට අනේ මගේ පළවෙනි පන්තියට ආවේ ළමයි 3 දෙනයි. මට පන්ති කාමරයක් දුන්නෙත් නෑ අප්පා. මට ගම්පහ ඉන්දීපේ කොරිඩෝ එක පොඩි වයිට් මේ වයිට් බෝඩ් එකේ මේ ග්‍රීන් කලර් බෝඩ් එකක් දීලා මුණු කැලි ටිකක් දුන්න පුළුවන් විදිහට කියන කන්ද කියලා. අර කොරිඩෝ එකේ බංකුවක් තියලා. අපි එහෙමයි පන්ති පටන් ගත්තේ. මේ පටන් ගන්න ගමන් ළමයි 100 200 පන්ති වලට අපි ආවේ නැහැ. මන්න කාමරේ හිතා ගන්න බෑ. මූණ බලන්න ආසයි වගේ මැසේජ් දානවද කියලා ළමයිට ගුරුවරයෙක් කියන එක. අනිත් එක වගේ හිරිවැලි කෙල්ලෙක්ව තියාගන්නවද හරි අමස්ල කෙනෙක් නම් ක්ලාස් ඇඩ්මින් විදියට. යා. මම දන්නේ කවුද යන්නේ කියලා පට්ට ආතල්ලේ කතාව මට ඒක මේ නිකන් කියන්නේ දුන්නේ. රයිට් අපි පාඩමට යමු. කොහෙන්ද නැවතුනේ අපි? From this equation, right? Please write special notes. Special notes. Under special note, write the first thing. Cooling correction. Cooling correction. Right. So what is cooling correction here? What is cooling correction? So I have told you that we start the practical with cool water. We send steam to cool water, then the temperature of cool water increases. So cooling correction means something like this. Look at board carefully. We start the practical, let's say room temperature is theta degree Celsius. What is theta degree Celsius here? Room temperature. Room temperature. Initial temperature theta 1 degree Celsius. Theta 1 degree Celsius equal normally theta minus 5 degree Celsius. Can you understand it? Can you understand? Room temperature theta. Starting temperature of water is less than theta, that is theta minus 5. Board is inclined. Oh, my letters are inclined. Right. Come on, it's okay. Right. So this is the initial temperature. This is the initial temperature. Right. So for example, if the starting temperature is 30, if the room temperature is 30 degrees Celsius, the starting temperature is 25 degrees Celsius. If the room temperature is 30 degrees Celsius, the starting temperature will be 30 minus 5. It means 25. Starting temperature will be theta minus 5 degrees Celsius. Got it? So theta, if theta is 30, starting temperature will be 25. Right. Then we provide steam continuously until we reach the final temperature. Final temperature is equal to normally theta plus 5 degrees Celsius. So this is the final temperature. Can you understand it? So this procedure is called cooling correction. I have drawn cooling correction diagram. We start the practical few degrees, normally 5 degrees below the room temperature, and stop the practical once the system reaches 5 degrees above the room temperature. Clear? Then we should explain why we do such a thing. If we do something in science, there must be a reason for it. We start the practical few degrees below the room temperature. We stop the practical few degrees above the room temperature. There must be a reason for it. So we are going to find the reason for it. Okay, dear? Right. So please draw this diagram. After that, I'll explain. Draw this diagram here. Okay, dear? Right. So, the thing is this. There is a calorimeter. There is a calorimeter. There is some water. Listen to me carefully. I'm not in a hurry. Nobody can cover syllabus earlier than me, right? Still, other teachers are teaching still simple harmonic motion and sound waves. They have to cover light and they have to complete these 10 practicals. So far, I have completed 3 practicals. I have completed 90% of heat theory. 90% of heat theory. I just want to teach only 7 more practicals. So I'm not in a hurry. The main thing is you should understand this. Whatever I teach, you should understand and you should reach to your goals. That's what I want there. Right. Look at what there is a calorimeter. It is filled with water. Right. There's a stirrer also. There's a stirrer also. Right. My question is this. Let us consider air. Let us consider this air around air, atmosphere actually. Atmosphere around this calorimeter, right? So I'm going to ask you a question. You should think well and you should tell me the answer. This is calorimeter. Calorimeter with water and steam, right? My question is, if the atmospheric temperature, or you can say room temperature, is 30 degrees Celsius. What is the room temperature? Listen to me carefully. Room temperature, this atmospheric temperature, 30 degrees Celsius. Temperature of calorimeter, temperature of stirrer, and temperature of this water. Temperature of this water is 25 degrees Celsius. Temperature of this calorimeter and its contents 25 degrees Celsius. Temperature of the surrounding air 30 degrees Celsius. Then what will happen? Will heat energy flow from calorimeter to air or air to calorimeter? Send you answers to my Zoom chat. I want to check one by one. What will happen here? Yeah, I ask you the temperature of air 30 degrees Celsius. Temperature of water and calorimeter 25 degrees Celsius. So my question is, will heat energy flow from calorimeter to air or air to calorimeter? Send your answers to my Zoom chat. I want to check. Oh, very good. Very good. All the students send me the answer saying heat energy will flow from air to calorimeter because temperature of air 30 degrees Celsius, temperature of calorimeter 25 degrees Celsius. So heat energy will flow from air to calorimeter. Now my question is, listen to me carefully. The temperature of air is still 30 degrees Celsius. Now temperature of calorimeter is 29 degrees Celsius. Then what will happen? Will heat energy flow from air to calorimeter or calorimeter to air? Right. Send your answers to my Zoom chat. Will heat energy under these conditions? Will heat energy flow from air to calorimeter or calorimeter to air? right? I have asked 2 questions so far. My third question. Now temperature. Now, right? Now my third question. Therefore, what will happen in this region? If you consider from theta 1 to theta degree Celsius, theta 1 is the temperature of calorimeter, water and steam. Theta is the room temperature. It means theta is the temperature of the atmosphere. So my question is, during this period, during the temperature of calorimeter increases from theta 1 to theta degree Celsius, will heat energy flow from air to calorimeter or calorimeter to air? Somebody unmute the mic and tell me. May I repeat the
From air to
question?
calorimeter.
Yes, dear, yes, again.
From the air to the calorimeter.
From air to the calorimeter. Very good. So during the time period, while the temperature of calorimeter and its contents increases the temperature from theta 1 to theta, heat energy is absorbed by the calorimeter. Air gives heat energy, calorimeter and its contents absorb heat energy from the surroundings. Air, atmosphere, and please use another term. Please use another term, surroundings. 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 Please mark it with surroundings. Surroundings. area. Surroundings, right? So star point and right. I'm going to explain this cooling correction. These things are asked in the examination. Therefore, you must have a clear understanding about this. Star point and right. Initially, sorry, during the time period, that the temperature of calorimeter, during the time period that the temperature of the calorimeter increases from, during the temperature of calorimeter increases from theta 1 degree Celsius to theta degree Celsius, during the time period that the temperature of the calorimeter increases from theta 1 degree Celsius to theta 2 degree Celsius, during the time period that the temperature of the calorimeter increases from theta 1 degree Celsius to theta degree Celsius, comma, the calorimeter absorbs heat energy from the atmosphere. 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 Right? So I would like if somebody unmute the mic and read that note.
During the time period that the temperature of the calorimeter increases from theta 1 degree Celsius to theta degree Celsius, the calorimeter absorbs heat energy from the atmosphere.
Thank you, Ria. Thank you very much. Now my question is, let's say, now the temperature of the calorimeter is 31 degrees Celsius. We are continuously providing steam, right? Steam is at 100 degrees Celsius. So when we provide steam to water in calorimeter, temperature of calorimeter, water and temperature steam still increases. So now the temperature of the calorimeter and its contents 31 degrees Celsius. Temperature of the surroundings air 30 degrees Celsius. Now, what is the direction of flow of heat? Will heat energy flow from air to calorimeter or calorimeter to air? Somebody unmute the mic and tell me.
Calorimeter to air.
Calorimeter to air. Very good. So as the temperature, now the temperature of calorimeter and its contents larger than the temperature of the surroundings air. Therefore, heat energy will be given from calorimeter to air. So my final question is, during this time period, what is the direction of flow of heat? When the temperature of calorimeter is bigger than theta degree Celsius, right? So still we provide steam, therefore temperature of calorimeter increases by passing theta degree Celsius. Theta degree Celsius is the room temperature. So when the temperature of the calorimeter increases from theta to theta 2 degrees Celsius, during that time period, will the heat energy given out by calorimeter or absorbed by calorimeter? What's the direction of flow of heat? Calorimeter to air or air to calorimeter? Somebody unmute the mic and tell me.
Calorimeter to air, sir.
Calorimeter to air. Very good. So next star point. During the time period, star point and right. During the time period that the temperature of calorimeter, increases from theta to theta 2 degrees Celsius. During the time period that the temperature of calorimeter increases from theta to theta 2 degrees Celsius, heat energy is given out by the calorimeter. To the surroundings. Heat energy is given out by the calorimeter to the surroundings during the time period that the temperature of the calorimeter increases from theta degree Celsius to theta 2 degree Celsius. The calorimeter gives heat energy out to the surroundings. During the time period that the temperature of calorimeter increases from theta degree Celsius to theta 2 degree Celsius, the calorimeter gives heat energy to the surroundings. Clear? Right. Who would like if I repeat the statement? Anybody in the class? Right. Okay, no need. Right. So listen here. From theta 1 to theta, during this time period, calorimeter absorb heat energy from the surroundings. From theta 1 to theta degree Celsius time duration, calorimeter absorbs heat energy from the surroundings. When the temperature increases, during the time period that the temperature increases from theta to theta 2 degrees Celsius, calorimeter gives heat energy out to the surroundings. Initially absorbed, finally given out. Therefore, this gap is same. 5 degrees Celsius, 5 degrees Celsius. Theta to theta 1, 5 degrees Celsius. Theta to theta 2, 5 degrees Celsius. Therefore, it is clear that during heat energy absorbed during this time period is equal to the heat energy given out during the final time period. So Finally, we can assume that heat energy absorbed from the surroundings is equal to the heat energy given out to the surroundings. Star point and right. Finally, the amount of heat energy absorbed from the surroundings. Finally, the amount of heat energy absorbed from the surroundings, the amount of heat energy absorbed from the surroundings, comma, is equal to the amount of heat energy, is equal to the amount of heat energy given out to the surroundings. Finally, the amount of heat energy, absorbed from the surroundings, comma, is equal to the amount of heat energy given out to the surroundings. We'll stop. Therefore, the total heat exchange with the surroundings. Therefore, the total heat exchange with the surroundings is 0. Therefore, the total heat exchange with the surroundings is 0. Total heat exchange with the surroundings, sometimes said to be net heat exchange. Net heat exchange. Therefore, the total heat exchange with the surroundings is 0. Full stop. Then it can be neglected. Full stop. Then it can be neglected. The amount of heat energy lost to the surroundings. Then it can be neglected. The amount of heat energy lost to the surroundings. Okay. The above process is known as a cooling correction. It's better if you use a different color pen to write cooling correction. It's better if you use a different color pen to write the cooling correction. So the above process is known as a cooling correction. The above process is known as a cooling correction. Right. Is it clear here? Is it clear for all? Right. Number 2. Special note number 2. I have explained this number 2 point while I was discussing the tail, so I'm not going to explain it. I have explained this number 2 while I was teaching the experiment, so I'm not going to explain. I'm just giving you the note number 2. Special note number 2. 2 tubes are connected to the boiler. 2 tubes are connected to the boiler. I think you remember. 2 tubes are connected to the boiler. Full stop. One is used to take steam out. 2 tubes are connected to the boiler. Full stop. One tube is used to take steam out. One tube is used to take steam out, and the other one is used for the safety of the people who carried out the practical. One is used to take the steam out, and the other one is used for the safety of the people who carried out the practical. Right? So one tube is used to take steam out, the other one is used to take is used for the safety of the people who's carried out the practical, right? So I explained completely, so I'm not going to explain it any further. If you want to know more details, please read last week note. Number three, an insulating sheet is kept between the calorimeter and the burner. A heat shield is kept in between the calorimeter and the burner, within brackets boiler, both boiler and burner at one side, calorimeter is at the other side. Between them, a heat shield, right? An insulating sheet is kept in between burner and the calorimeter, comma, to stop the direct heat flow, from burner to the calorimeter. An insulating sheet is placed between the burner and the calorimeter, comma, to stop the direct flow of heat from burner to the calorimeter, right? Otherwise heat will flow from burner to the calorimeter directly. Therefore, temperature of calorimeter directly increased. So we should stop it. So I have named it as heat shield last week. Okay. The final special point is number 4. Do you remember this term here? Do you remember this term? Right. File number 4. A steam trap is used. 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 A steam trap is used to remove the liquid water, drops coming with the steam. A steam trap is used to stop liquid water drops coming with the steam. Full stop. It prevents hot water drops entering to the calorimeter. It prevents hot water drops entering to the calorimeter. It prevents hot water drops entering to the calorimeter. Full stop. It is used to obtain only steam without any liquid water. It is used to obtain steam without any liquid water. It is used to obtain steam without any liquid water. Okay, dear? Right. Somebody please read special note number 4 once again. Somebody unmute the mic and read special note number 4.
A steam trap is used to remove the liquid water drops coming with the steam. It prevents hot water drops entering to the calorimeter. It is used to obtain steam without any liquid water.
Thank you, dear. Thank you very much. I would like to hear the voice of one more student. Thank you for the first one, and I would like to hear the same note from one more student. Somebody unmute the mic and read.
A steam trap is used to remove the liquid water drops coming with the steam. It prevents hot water drops entering to the calorimeter. It is used to obtain the steam without any liquid water.
Right. Thank you, dear. Thank you very much. Right. So that's all I wanted to teach about this practical. If you want, you can do this figure also. Now let's try to discuss a past paper question. That's all I want to teach you about this practical. So if there are any other things we may learn while we are discussing past paper questions. There are many past paper questions given from the same practical. Let's try to do one of them. Let's try to discuss one of the practicals given in the one of the questions given in the exam from this practical. Let's give a try here and give me 1 minute to find the question, okay? Okay, I'll show you the question. That question was given in, let me show you. Right.